So this is our last lecture, our third and last on psychrometrics. Let's start off with this. We want to justify the assumption that water that is in saturated air at 30 degrees C behaves as an ideal gas. So what does it mean to behave as an ideal gas? It basically means three things, but the one that is pertinent right now is that the pressure times specific volume is equal to RT. It obeys the ideal gas equation. So if we think about it, it's like the temperature specified and it's saturated air. So in a sense, the vapor pressure is also specified. The partial pressure of the water vapor in the saturated air is specified. So what we can do is we can check V to see if it's close. Close to what? Well, you can calculate V from the ideal gas equation. That would be R. Let me put R bar T divided by partial pressure of vapor in the moist air times the molar mass of water vapor. You can calculate it assuming it behaves as an ideal gas, and then you can compare it to see how well it compares with the specific volume out of the tables for the saturated vapor. Put V sub G out of the tables. If they compare, that's a pretty good justification. Okay, so what do? We go to the 30 degrees C and we pick out the partial pressure and some numbers here. Yep, this slide, this one right here. So we pick out that it's 4.246 kilopascal. The molar mass to 18.02 kilograms per kilomole for the molar mass. Then 8.314 kilopascal meter cubed per kilomole Kelvin. And then the temperature, 30 degrees C, it becomes 303 Kelvin. So you can compute that specific volume is 32.92 meter cubed per kilogram. We go to the table. V sub G at 30 degrees C is 32.894 meters cubed per kilogram. And you say, are they close enough? And they are. What's the difference? The difference is V sub G minus V sub IgE divided by, let's normalize it. So we're interested in the absolute value of the difference. Normalize it with the value we think is the most accurate out of the table for the steam tables. And you find that that's 0.8%. As an engineer, what do you think? 0.8%? Negligible. It's pretty good. So you can do this at, yeah, that's PSAT right there at the 30 degrees because it's saturated air, right? And then you can do this repeatedly and plot it on a temperature volume diagram. Because the specific volume ranges over such a large range that we plot it on a log scale. This is our traditional dome. Out here is the states of saturated vapor. True? Along that line. Out here we would definitely agree that it behaves as an ideal gas. Way far away from the dome. If you get close to the dome, near the critical point, the error is quite large. It's up in the 10% plus range. So don't apply the ideal gas model for water vapor even close to the dome, but up near the critical point. But if you come down here, what you find is at low pressures, low temperatures, it's less than 0.1%, even right up to being saturated vapor. And that's really a startling result when you think about it. Really? It's ready to condense, and yet the water vapor still behaves as an ideal gas. And that's how moist air is. It has water vapor, it behaves as an ideal gas. So this justifies that ideal gas approximation. How many people were probably troubled by that, right? You thought, yeah, it's like, does this really make sense? Even saturated air, close to that liquid forming, that water condensing, yes, it's true. So this plot is done to scale. I think I did it in MATLAB, and it took me a long time to do it, but it's true data, okay? It's true data. All right, let's press forward. you've all been around air compressors. This is a little pancake air compressor. It's got a 5-gallon storage tank. Right down here is the shape of it. And you can look at these at Home Depot. Probably most of you have used air compressors, but this one's so cheap you can lift it and hold it. There's a little tube that comes out of the compressor section, and then it dumps the air into the tank. All right? Where does it get the air from? The room. So if it's in the garage, it draws the air from the garage. If it's outside, that's where it draws it in. Probably some of you have a little bit of experience with this air compressor. If you touch this tube right here, it's typically not insulated, but if you touch it, will it be warm to the touch? It'll be hot. It'll be hot to the touch. You can even burn yourself, because what happens when the motor is compressing it and the air is behaving like an ideal gas, the temperature goes way up. True? All right. Just like a good engineer, you actually read your owner's manual. I know the other people just throw them away, but you read them. I read them too. They're kind of interesting reading, because you learn a lot of stuff. But right in here they have air compressor safety. Ah, you got my attention. And so in here they have safety information. They have 8 points. Let's not go all through all 8, but the 8th point, what does it say? Drain tank daily or after use. Internal something causes tank failure and some like explosion. I think I truncated it. So what's going to happen if you don't drain your tank? You get rust. And it could lead to tank failure. Well, I've never seen one of the compressors have tank failure because of rust. Anybody seen that though? All right, well, okay. How many people have seen this and know that you need to drain your tanks on the air compressors? Just a few? Really? Well, I had a student in the class a couple years ago, and he said it cost his dad for a different reason. He didn't have a dryer on his compressed air system, and he had a number of tools, and they would continue to fail. It was like, you got to put a dryer on that. And so he convinced his dad, and he did, and the tools quit failing in his shop. But anyway, so they have a little cock right down in here on the pancake type. You can see it in this illustration. It's item number 8. You come down, look at that. Item number 8 is drain valve. For those that use the drain valve, what actually comes out? Can you describe it? Nasty, rusty, red-colored water, right? So you see that it's rusting inside the tank, but it's water that comes out. So the first time you see that, or probably when you're young, you're just dumbfounded. Water? Who put the hose? Where'd the water come from? Well, in this class, we can predict it, right? Where did it come from? From the moisture in the air. You have a really hot, warm, humid summer day, you got to be careful with that tank. You live in El Paso, not so much of an issue. You live in Houston, you have a big issue. Our friends are back, huh? So let's do this. Let's analyze this problem. Moist air is taken into the air compressor. It's then compressed, and then it's stored in the tank. So I'm thinking about state 1, where it's initially the air is outside the tank. It's in the room, in the garage. Then it's promptly compressed. And now it's like in that tube. If you touch it, what will happen? You'll get burned. Okay? And then finally, after a long time, state 3, it's stored in that tank, let's say 24 hours later. What do you think is going to happen to the air temperature that's in that tank after 24 hours? It's going to cool back down to the atmospheric room temperature. Now, what will happen is as it cools, the compressor pressure, the pressure will drop in the tank, the compressor will kick back on, and it'll make sure the pressure stays there. So I'm going to think about constant pressure cooling. I know that's a little skip, not constant volume cooling, but constant pressure cooling in that tank. But let's do this. Let's talk about what is the temperature doing. So we have the temperature in the room before it went to the compressor. Then we have the temperature immediately after it's compressed. What do you think the relationship between this temperature and that temperature is? One's high? That's right. This one's spanking hot. Now we wait a long time. T3, what do you think T3 is? Back down to T1. And you got to get the temperatures right in your mind. Okay? The second, easy pressure. So we have the initial pressure outside. atmospheric pressure. We dump it in, we compress it. Well, how high do you think the pressure is in a tank, compressed air? 120 psi. Absolute or gauge? Gauge, add another 15. Get the total on that, 140-ish. Divide by 15. You can get how many ATMs there are. It's about 9, 8, 10, somewhere in there. I think on the next slide I use one where it's 800 kilopascal. So it starts 100 kilopascal and is now 800 kilopascal. So the pressure's up. What about the pressure at state 3? How is it? Is it related back to, is P3 equal to P1? No, it's P2. It remains constant. All right. How about the density? This is a little trickier. So we're talking about the density outside. You then ingest it, you compress it. Density at state 2, how does it compare to density at state 1? Much greater. Now, I know this is a little tricky, but we're going to cool it at constant pressure. What do you think the density is going to do? It's still greater, but as you cool it, it'll even get even greater because the compressor will have to kick in and throw more in there to keep it that high pressure, right? All right. How about omega? I forgot. What is omega? Humidity ratio. What's it defined as? The mass, like kilograms of vapor to the mass of dry air. So let's say we have some humidity ratio outside in our garage. Some more humid day, it's a higher value. But now we stuff it into the compressor right immediately after. How does omega 2 compare with omega 1? You have 3 choices. It's either greater, it's equal, or less. Who said same? It's the same. Think about it. I ingest so much air, that's what I'm trying to get in there. Water vapor's coming with it, but this proportion doesn't change even though I compressed it. The temperature's way up, the pressure's way up. Does that make sense? So omega is the same. How about after I let it cool for a while? Depends. Am I going to get a little liquid in the bottom of the tank or not? Yes. If I definitely get liquid in the bottom of the tank after it cools, the humidity ratio will go down. If I don't get any liquid in the bottom of the tank, then it'll be the same. But it'll go down because of condensation inside the tank. So this is, it goes, let me just draw omega 3 and this is greater. So this goes down. Okay, how about the relative humidity? I saved the hardest for the last. All right, relative humidity is 50% in my garage. All right, I put it through the compressor, and I want to know immediately after it jumps that pressure way up, what happened to the temperature again? Way up. What happened to the relative humidity? Way down. You don't have a condensation problem right after it's compressed. You have a condensation problem after it sits there for a long time. The relative humidity, state 2, goes way, way down. Why again? Well, what is that equal to? Isn't it the partial pressure of the actual vapor divided by, and doesn't the saturation pressure when the temperature goes up go up rapidly? And that's really why it goes down, down, down. Now, let's say I waited a long time, it's cooled, and actually a little condensate is formed in the bottom of the tank. What's the relative humidity? 100%, isn't it? Because it's saturated air. True? Very good. Now let's put some numbers to it, now that we have the concepts right. So we have moist air at 25 C, 100 kilopascal, 50% relative humidity. It's compressed to a final pressure, 800 kilopascal. What is the final temperature immediately after it's compressed? Professor, I paid UTSA all this money in tuition. I sat through all your classes. You know how to calculate this, don't you?
It's just like the gas.
Yeah. Ideal gas, even though it's a mixture of air and a little bit of water vapor. But if you just wanted to make a quick calculation, I would do this. I would say the final temperature after compression is the initial temperature after compression, P2 over P1. How much? What was the pressure increase? To the K minus 1 over K. True? And you can do a lot of work to get the K of the mixture, and you can compare that to the K of the dry air, but because there's just not that much water vapor in the air that we breathe, remember by mass, we had a really moist system, and it was like 1 or 2%, that's pretty moist, that this basically is going to be around 1.4. So we put in the absolute value of temperature, and we can calculate that that temperature at 2 coming out is 200 and around 70 degrees C, and that's for a perfect compressor where isotropic efficiency is 100%. I know I rounded off to 2 significant digits. If it wasn't a perfect compressor, do you think Home Depot is going to sell you a perfect compressor? No, it's not isentropic, so it's even going to be higher, isn't it? It'll even be higher. But we can use that, and what we can do is make the calculation here. What is the humidity ratio after you compress it at omega 2? How would I calculate omega 2? It's equal to omega 1. Didn't we just talk about that, right? So all I have to do is calculate omega 1. That's whatever humidity is and outdoor temperature and outdoor conditions. So it started with 25 degrees C, 50% relative humidity. I think you can make that calculation. It comes in at 0.01. If you want more digits to it, it's 0.014 kilogram of vapor per kilogram of dry air. I would be repeating myself if I showed the calcs. But again, how did that do? That's 0.622. Vapor pressure over P minus PV. True? And how'd you get PV? Relative humidity times Psat at that 25 degrees C dry bulb temperature. So we got that down. And omega 2 is equal to omega 1. So there's your answer for part B. How about for part C? What's the relative humidity right after? Well, Phi2 is equal to PV at 2 divided by Psat at, this ridiculous 270 degrees C. But that's the actual temperature of the air. And you find that saturation pressure is like 5499 kilopascal. Is that above atmospheric pressure? 5,000, nearly 500 kilopascal. Is that above atmospheric pressure? A lot. Atmospheric pressure is only 100. So it's like that gas at that state can carry a lot of water. And then how do you calculate this actual vapor pressure at state 2? Well, actually, you go back to this equation again, right here. And you have the omega at 2 is equal to all this, and I want PV2, right? And so you can just do a little bit of algebra, and you get PV2 is equal to the total pressure of the mixture, P without a subscript, divided by 1 plus 0.622 times, or divided by omega 2. It's just algebra. But have you done that algebra? Does this resonate with you? Does this equation look familiar? Yeah, if you solve some of the homework problems. Struggle with it. So you can actually calculate the vapor pressure at state 2. It's 12.7 kilopascal. The ridiculously low humidity is 0.2 something percent. Relative humidity is almost 0. Makes sense? Now we're going to move to state 3 for this process. We've now calculated what happens at state 2. The air is going to cool. The compressor turns on so that the final pressure is maintained at 800 kilopascal. It's going to kick in every now and then as it cools. But eventually the whole content of the tank's at 25 C and 800 kilopascal. What is the final humidity ratio omega 3? Well, you could start by saying, I'm going to assume that nothing condenses, and then I'll make some calculations. And when you do that, you can calculate the partial pressure of the vapor at 3, and then you can calculate the relative humidity at 3. It'll be greater than 100%. So it wasn't a good assumption that nothing condenses. So now what you'll do is turn around and say, no, I'm going to assume the relative humidity is 100%. Does it logic make sense? I'll assume nothing condenses, then say absolutely has to condense. Now I'll assume that it condensed, and what I have left in there is saturated vapor at 100% relative humidity, or saturated air. So then what is the actual PV at 3? P sat at the 25 degrees C, isn't it? And then what is then omega 3? All we do is use the same equations back and forth again, right? 0.622 PV3 divided by P minus PV3. But what is that P right there? It is your 800 kilopascal. Omega 3 comes in at 0.00247 kilograms of vapor per kilogram of dry air. The difference, the omega 2 is greater than omega 3, that's actually how much liquefies. That's the mass that liquefies of the vapor that turns to liquid water divided by the mass of dry air, and it's 0.00754 kilograms that turn into liquid per kilogram of dry air. And so essentially about 75% of the water in the vapor form that you ingested into the compressor and then boosted the pressure and then let it cool, 75% by mass will condense under these conditions. That's a lot. Only 25% stays in the vapor form. And the last question, what's the final relative humidity? Isn't it 100%? All right. Very good. Ready to press forward? Let's talk about the psychometric chart. It's in the back of our textbook, and you'll notice that they have it in SI and English units, but there's something very important in the title for this figure. The psychometric chart at 1 ATM, at 1 ATM. This chart's only good for 1 ATM. Well, we spend a lot of our life at 1 ATM, right? But if you do something in, let's say, Denver or mile-high cities, high altitude, then you have to adjust and get a different psychometric chart. They have a psychometric chart for high altitudes. All right, let's press forward. This is the psychometric chart. Did you already read about it? Struggle with it? Let's do a quick overview. What's on the x-axis? Dry bulb temperature. What's on the y-axis? Humidity ratio, but hey, usually we put the y-axis on the left side, but there's nothing. You can put the y-axis on the right side. So right here is the y-axis on the right side. Humidity ratio omega. So if somebody says I'm at this dry bulb temperature right here, and at this humidity ratio, you come out and find the point where it intersects. And how many temperatures did we have? We had temperature dry bulb, temperature wet bulb, temperature dew point, true. And how many humidities? Humidity ratio and a relative humidity. And then we also are interested in the specific volume. And so what is this chart when you get good at it? Here I just gave you, let's say this is a known humidity ratio and the dry bulb temperature. You can get the other ones. You can get the other ones. So now it's a little tricky, but let's take a look. These are lines of constant relative humidity coming up. So closely, just approximately, what's the relative humidity at that point?
40.
Around 40%. True? All right. All right. Now, what's the specific volume? That may be the next easiest. Well, where are lines of constant specific volume? This is a line right here of constant specific volume. True? And right here is one, a constant specific volume with a number, and here's another. So what can you read off what that specific volume would be? Yeah, so it's 0.85, 6, 0.87, then 8, 9, 90. So it's 0.87, 0.87. What are the units? Meters cubed of the mixture per kilogram of the dry air. Those were the easy ones. The wet bulb. Lines of constant wet bulb temperature are sloped like this. Like that. Does that make sense? So, you take a look. What do you think about this wet bulb temperature? Looks like it's around 19.5, 20 degrees C. That's what the wet bulb is. So the wet bulb for this was around, I'm just going to say 20 degrees C. All right, now I need to clean up the plot a little bit. Dew point. Can you get the dew point temperature for me? Exactly. Just go like that. All right, conceptually what you do is you cool it, and as you cool it, the humidity ratio doesn't change. It's going to stay the same. But what's happening? You go from 40% to 50% relative humidity, 60% relative humidity. You continue to cool it 70, 80, 90% until you get to 100% relative humidity. Conceptually, you just drew a straight line over till it hit to be 100% relative humidity. And then you can just kind of read down or read over. What does the temperature look like for the dew point? 13 degrees C. That's right. Now there's one other one, and it's the specific enthalpy of the moist air. If you solve a number of these problems, it's convenient to introduce not just the dry air humidity enthalpy, but also the humidity ratio times the enthalpy of the vapor in that mixture. And so they basically said this is the definition of H of the mixture. That this moist air enthalpy includes the enthalpy contribution from the vapor and what makes sense, the dry air. Most people will make the mistake and say, if they make a mistake, they'll say, oh, that only includes the dry air enthalpy, but it doesn't. It's the enthalpy of the moist air in kilojoules per kilogram of the dry air. It includes the vapor contribution to the enthalpy. And for introductory purposes, the lines of constant enthalpy, you can see this scale out here as your enthalpy scale, are parallel to the lines of constant wet bulb. You want to get more sophisticated? There's a slight difference in the slope, but look, for introductory purposes, it's the same. And so they push it out here so it's easy to see, and then they use these straight lines so you can extrapolate down into the chart. So you could actually read off the enthalpy at this state. What would it be? Looks like it's around 56 kilojoules per kilogram of dry air. You ready to solve a problem using the psychometric chart? I think this problem, moist air at 30 degrees C and 1 atm and 30% relative humidity with this volumetric flow rate flows over a cooling coil. It exits at a temperature of 15 degrees C. Now, unfortunately, I'm going to have to jump to another slide and back and forth as we work this problem. But it's 33 dry bulb, 30% relative humidity, and they give us a volumetric flow rate. The first question they're going to ask is, what's the relative humidity at the exit? We'll have to deal with that. The heat transfer from the air, and the mass flow rate of dry air, and then the rate of heat transfer from the air. So those questions. Let me jump over here. So there's 33 right here, isn't it? 33 dry bulb. What was the relative humidity? 30%. Right there's the intersection. We're not going to try and do this too carefully or too accurately. We're going to get 2 significant digits, and that's about it. And you're going to put it to a cooling coil. As you put it to a cooling coil, it will not condense immediately, it'll stay at the same humidity ratio, but it'll just drop the dry bulb as it goes across that cooling coil. And where did it say it stopped cooling at? At what temperature? 15? Is this 15C right there? And so if you just stay horizontal and you come across to 15, you stop at 90% relative humidity. Did any liquid or water turn into liquid? Did any vapor condense? No. No. Let's say somebody changes it up and says you cool it to 8 degrees C. Well, you're going to get all the way to 100. You'll hit the dew point. The dew point looks like it's around 13 degrees C for that condition. And then as you cool to 9 or to 12 to 11 to 10 to 9 to 8, what's going down? Humidity ratio is going down. You're getting that water out. It'll be condensing. Okay? All right. So with that, we know that we don't condense. We're stopping right here at state 2, and this is state 1. All right. Come back here. What is the relative humidity at the exit? Phi2, we just read that off the chart. 90%, true? What is the heat transfer from the air in kilojoules per kilogram of dry air? What are they asking me for part B? Change in enthalpy, that's right. So it's going to be, depending if you want a positive answer or a negative answer, the first enthalpy is higher, and then the second enthalpy is lower. I like to work with positive entities, so this will be a cooling. And so what I have to do is come over here, and I have to read off the enthalpy at state 1. That looks like it's about 57. The enthalpy at state 2, 39. And so the difference, somebody do the difference for me. 18? Is it 18? So the answer is that it's 18 kilojoules per kilogram. Is it kilogram of the mixture? No, it's a kilogram of per dry air. They like to work in dry air. It's easy. So that's the change in enthalpy. Oh, which I should have changed the symbols to Q, lowercase q, which is the heat transfer per unit mass, which is equal to the change in enthalpy. Okay. What is the mass flow rate of the dry air? So we want to calculate the mass flow rate of the dry air. They gave us the volumetric flow rate, AV, at 1. We divide by the specific volume at 1. So the specific volume at 1 is, it's right here, this line. And so it's 0.8567, 0.88, oh no, 0.87. What is it? 0.86 or 0.87? This is 0.85 and this is 0.90. .88. So you'll have 0.47 meters cubed per second, 0.88 meters cubed of the mixture per kilogram of dry air, and you can calculate the mass flow rate of the dry air. Part D, what is the rate of heat transfer from the air? Q dot. Wouldn't it be the lowercase q, the answer for part B, times the mass flow rate of the dry air, the answer from part C? Sure is. So in the interest of time, well, let's move on. You ready? All right. This was the homework problem that you did. We can solve this one, or we can solve that homework problem. I don't think we can solve both of them. This one? Look good? All right, let's solve this problem. So we have moist air at 27C, 1 ATM, 50% relative humidity, enters an evaporative cooling unit that operates at steady state consisting of a heating section followed by a soaker pad evaporative cooler. Well, I know that the difficulty in these words, but basically you're going to have a heating section as well as you're going to introduce some moisture. You could spray it in, or the air could flow over something that's soaked with the liquid. And that's a pad that's soaked with the liquid. And it's going to be evaporating adiabatically. The air passes through the heating section is heated to 45. So what they do is they give you some intermediate information. So this would be state 1, this would be state 2, then this is state 3. And they're saying that the temperature at 2, maybe I'd do it this way, put a table together. Temperature at state 2, this is 1, this is 3, is 45 degrees C, where it came in at 27 degrees C. And the relative humidity was 50% when it came in. And that doesn't tell me any more than it's just heated till 45 degrees C. Next, the air passes through the soaker pad and exits with a relative humidity of 50%. So I organize the information that's given. The first question is determine the humidity ratio of the entering moist air in kilogram vapor per kilogram of dry air. That look good? Okay. So how am I going to calculate, let's say omega at state 1. Right. And the partial pressure of the vapor at 1 is the relative humidity at 1 times P sat at the temperature dry bulb at 1. And so we look up P sat at that 27 degrees C. Let me see if I find my numbers. And it looks like that's around 3.567 kilopascal. So the vapor pressure is 50% of that, 1.7835. And then the omega is 0.1114. So here if I want omega 1, I box it. Are there any units on it? Well, it's kilogram per kilogram, so you don't need to put a unit on it, or you could put kilogram vapor per kilogram dry air. Either way. That's the answer for part A. I did it a little fast because I think most of you were able to solve that part. Part B. What is the rate of heat transfer to the moist air passing through the heating section? So what is this Q dot coming into the moist air? But they want it lowercase q. It's kilojoules per kilogram. Now, I didn't like the way the book put it, but the book actually said per mixture. And we can adjust. It's a little itty-bitty trivial adjustment, but basically almost all of it is dry air. Okay? And I think it's more of a typo of the textbook. But let's solve it for the kilogram of dry air. Wouldn't that be then lowercase q is equal to the enthalpy coming out at 2 minus the enthalpy of 1? True? And so we go to a psychometric chart and we say, where are we at? We're at 27 and 50% right there. And where are we at after we go through? We're at the constant humidity ratio, 0.1114. And we're going to come out at what temperature? We're going to come out at a temperature of 45, which is right here. So there's state 2. State 1 to state 2. Now I have to read off that enthalpy. And I'm going to say that's 74. And read off that enthalpy. 56. And 74 minus 56, close enough. Okay. So what answer did that give me? Come back here. So I actually, the enthalpy at state 1, 74, then it's 56, and so this is whatever it is, 74 minus 56. something. You got around 18? Okay, fine. 18 kilojoules per kilogram of dry air. Somebody says the book said it's per kilogram of the mixture. I want to make an adjustment to that. Well, first of all, we're fooling ourselves if we're going to use a psychometric chart. You're not getting 3 significant figures. Get the computer program if you want it that accurate, right? So, but it's not that hard to do. So how do you make that adjustment? So you say, I have the mass of the mixture is equal to the mass of the dry air plus the mass of the vapor. True? So if we divide the, you have the mass of the dry air is equal to 1 plus the humidity ratio. Does that equation look good? So if I wanted to multiply by the mass of dry air divided by the mass of the mixture, then I would take this 18 and I would multiply by 1 over 1 plus omega. Did I do that right? Yeah. And there you go. How many people struggled with that? My apologies. The textbook is really a typo. Did I tell you the student that I had many, many, many years ago in Thermo 1? Right? Did I tell you this story? So it said in chapter 1 or chapter 2, and every problem had, oh, and G is 9.81 meters per, what is G again? Meters per second squared. And sure enough, and I loved it, they had this typo in about 6 editions of the, so one problem in chapter 1 had G is equal to 9.81 meters per second. No squared. And some poor student, just couldn't figure it out and struggled, and he complained to me. I wasted over an hour of my life. I was trying to solve this problem, and it's not solvable. And I said, well, just look at the line above and the line above and the line above, and it's a typo. And I do remember when I was an undergrad student and I found typos in the textbook. And it's like, hold it, I paid over, well, at that time, about $80 for a book. You paid over $220, didn't you? You feel cheated. But anyway, there are typos in books. There's not that many typos in this book, but there's other books that have a lot of them. So anyway, I apologize. It was a typo, and I didn't see it before the problem was issued.
I'm a little confused with what you just did.
Well, I want to put it in kilojoules per kilogram of the mixture. Kilogram of the mixture. And so what I have is maybe I should have done another step. This equation is the mass of the mixture is equal to the mass of the dry air times 1 plus omega. So the mass of the mixture is going to be, maybe it's mix MIX, and then the mass of dry air, right? So that's equal to 1 over 1 plus omega. Did I do the algebra correct? And so then I said I want this to be in terms of not per kilogram of dry air, so I'll have to multiply by that. Well, it's multiplying by 1 over 1 plus omega. So if we calculate it, I wrote that omega down completely wrong. Did you notice that? There's a lot of zeros missing. 0.014. There it is. I wrote it down correctly. So now, somebody take their calculator and do what is 1 over 1.01114. It's close to 1. It's really close. 0.9889, something like that. Yeah. So, okay. All right. Let's go to this one. What is the humidity ratio and temperature at the exit of the evaporative cooling section? What is the enthalpy of the liquid coming in? Huge or small? Very small, especially compared to the vapor. All right? So what you do is you write an energy balance. I'm running out of room. I need to scroll down, or maybe I should scroll up. Try that. So let's do an energy balance here. If I do an energy balance, I'm going to have the mass flow rate of the dry air plus or times the enthalpy of the mixture coming in. Okay. Let's do it at 2. So we're just going to go between 2 and 3. Okay, between 2 and 3. Plus the mass flow rate of the liquid times the enthalpy of the liquid. Isn't that equal to the mass flow rate of the dry air going out times the mixture enthalpy going out? Is this equation good? I just did it from 2 to 3. Right? The liquid comes in between 2 and 3, right, is added. Okay, I think this is a good energy balance, unless I have an error. Do you see an error, or is it good?
Where are your terms for the vapor?
The vapor is included in this enthalpy of the mixture on the psychometric chart, right? So guess what? If you do the mass flow rate of the dry air, basically H2 minus H3 is equal to the mass flow rate. Well, I'm trying to get this. Basically, this term, well, how much liquid's entering? Not much. What is the enthalpy of the liquid? Not much. Guess how close H2 and H3 are to each other? They're the same, essentially. If you do the math, you get it just a little bit. So on the psychometric chart, what does a line of constant enthalpy look like? Where do I stop? They said they wanted to stop it at the humidity, relative humidity of 50%. Oh, it's too easy on a psychometric chart. You almost have to use software otherwise, true? Or iterate by hand. Oh boy, really hard. So anyway, there's state 3 on the psychometric chart. So you can answer the last question of the humidity ratio and temperature at the exit. So now we can pull off the humidity ratio and the dry bulb temperature. And it's around, what, 32, 33 degrees C. Thank you very much for your attention. Monday, exam.